We're going to tackle a couple of topics today. Uh, Last time we talked about the discovery of these different subatomic particles. We talked about the gold foil experiment with Rutherford. We talked about Thomson's experiments dealing with determining whether or not uh, electrons were being ejected from an atom or if the atom was actually divisible, which we found out, and we know now that it wasn't. Um, and so let's talk now about, so for today, we're going to talk about something a little bit different. Um, we're going to jump in. I think, did we talk about isotopes? The last time we met was the last Wednesday. Did we get to isotopes?
No, sir.
All right, so we're going to start out with that. That's the last, because that's going to give us an introduction to that last subatomic particle, which is a neutron. And then we're going to jump in and start talking about the periodic table and atomic structure and symbolism. So the studies done by Saudi. Let me just put right here. Put a heading up here. And this is 2/7/22. All right. So there was some work done by Saudi and James Chadwick dealing with the isotope. They were studying radium, and what they found was that there were some radium species that had the same exact atomic mass, but they had, they had the same exact atomic number, but they had a different atomic mass. All right. And so what was later discovered between the work of Sadi and Chadwick, and this was in 1932, what they found out was that there was actually another subatomic particle that existed and resided in the nucleus of an atom. And that particle is what we call a neutron. It's an uncharged particle in the nucleus of an atom. All right. The neutron itself helps to also account for the atomic mass because it has roughly the same mass as a proton. So it has the same mass as a proton. So most of your mass in your atom is going to be concentrated in the nucleus, and it's going to be a sum. The atomic mass is literally the sum of protons and neutrons. Electrons, the mass of an electron is so small that it doesn't really have any impact on the overall mass of an atom. All right. So again, this also led to another discovery. So the discovery of the neutron gave us what we call isotopes, right? These are atoms or elements that differ only in atomic mass. So it's the exact same element, but it has a different atomic mass. And we're going to talk about this quite a bit. So I'm not going to go into great detail right now, but we're going to talk about isotopes a lot, especially when we start calculating the average atomic mass. But an isotope of an element is the same element but the isotope is going to have a different atomic mass, and that's because of the neutrons in the nucleus. So the mass difference is due to additional neutrons. All right. So whenever you hear that term isotope, just know that an isotope of an element is an element or a how do I put this? An analog of that element that has a different number of neutrons in the nucleus. All right. So that's going to change the atomic mass. All right. So with that being said, now we've studied 3 subatomic particles. We've studied electrons, and we know how they were discovered using that cathode ray. We studied protons and how they were discovered using alpha particles. And now the neutron itself, which is another particle in the nucleus of an atom, was basically discovered when radium was being studied. And there were 2 samples of radium, but one had a different atomic mass. And so later, more experimentation and more studies led to the discovery of the neutron. So those 3 subatomic particles, very important. And with the isotope, that's going to be even more important, because even the atomic masses that we see those atomic masses are the result of basically an average of all naturally occurring isotopes, because every isotope is not present in the same amount in nature. All right, so we'll talk more about that a little bit later. So now we're going to shift gears and move into another topic, unless there's a question about isotopes. All right, so we're going to start talking about atomic structure and symbolism. And so with this, under this umbrella, we're going to talk about atomic mass, right? Atomic number, or Z. We're going to talk about ions and charges. We're going to define the AMU, or the atomic mass unit. And we're also going to talk about calculating the average atomic mass, which again is an average of all the naturally occurring isotopes. All right, so with those topics in mind, and with those subtopics in mind, let's jump in and let's start talking about the atomic mass of an atom. And again, when we think about the model for an atom, let me add another page here. I'm trying to keep that periodic table because we're going to talk about that shortly. When we talk about the model for the atom, we have this small nucleus, right? And then orbiting that nucleus, we have here electrons orbiting the nucleus. All right. And we know that the mass of the atom, again, is concentrated in the nucleus. I hate it when that happens. Right. So the protons and the neutrons that are in the nucleus, that's where the majority of your mass is going to be. And so atoms have, we're going to talk about some different characteristics of atoms. Obviously, they have a mass. All right, so let's talk about that. So atomic mass is defined by what we call atomic mass units. Right. And in chemistry, we need a reference. A lot of times we need reference points. And so the AMU is defined basically as one atomic mass unit is 1/12 of the atomic mass of carbon. Right. So 1/12 times the carbon atomic mass. Right. And that number comes out to be 1.6605 times 10 to the minus 24 grams. That's a very, very, very small number, but that's the equivalent for one atomic mass unit. It's 1/12 of the atomic mass of carbon, which is the number that we have here, 1.66 times 10 to the minus 24, and that's grams. So with that number in mind, we can also think about a conversion between grams and atomic mass units, right? So we can say one gram or one atomic mass unit is 1.6605 times 10 to the minus 24 grams. And then if we need to ever convert between those two, then this is what we can use, right? This is the conversion factor. So you ever need to convert between grams and atomic mass units, we have the numbers to do that. All right. Sometimes you'll see atomic mass units represented by different symbols or different units. Right. You'll see atomic mass units. An equivalent symbol for an atomic mass unit is a Dalton or a unified mass unit. So you might see the mass of an atom given in Daltons or in U's or unified mass unit, which is the symbol U. But those are all equivalent to AMU without any type of conversion necessary. So you can see you can see the atomic mass given in Daltons or U's or AMU. But for this class, we're going to stick to atomic mass units, AMU. All right, so the mass of any atom on the periodic table is given in atomic mass units. So those numbers that we've been working with our constant proportion problems and multiple proportion problems, all of those numbers, when we get the atomic mass, we're getting that in atomic mass units. And the reason why we weren't converting atomic mass units into grams in the case of those questions is because normally we were doing like samples of 100 grams or so and so number of grams. And so the numbers themselves, we just use as grams. So when we pull them from the periodic table, we just use as grams because all the problems involve some element or some atom of an element that we're trying to find out how much of that atom is in a particular sample. So that's why we didn't necessarily have to convert between grams and atomic mass units. So now let's talk about charge on atoms. All right. So an atom itself can be positive, it can be negative, right? Or it can be neutral. I'm going to abbreviate positive. You may not have ever seen this before, so don't panic. Or you probably have. So positive, negative, or neutral. For the record, most of the times, your atoms and different elements prefer to remain neutral. Anytime an atom has a charge, that atom is going to be considered slightly less stable than the neutral counterpart. All right. So within the atom, anytime an atom has a charge, it's going to be due to one or two things. It's going to be due to losing electrons, which we're going to talk about shortly, or gaining electrons. But for the subatomic particles within an atom, the proton has a positive charge, right? The electron has a negative charge, which we talked about already. And then the neutron has no charge, right? And then we even know what the charge on an electron is based on the work that was done by Millikan, right? We know that this is 1.602 times 10 to the minus 19 coulombs. So we know the actual charge amount for an electron, but again, the overall charge on an electron is negative. That was also based on the work done by Thomson, right? When he found that, used that cathode ray and found out that the particles in the cathode ray were attracted to that positive plate in his device that he was using. All right. So we know something about charge, and we're going to know something about mass. And now let's talk about atomic structure. So let me add another page here. Right. So for atomic, as far as atomic structure is concerned, right, we're gonna have two terms that we're going to be dealing with, and that is Z and A. Z is the symbol for atomic number. A is the symbol for atomic mass. Right? And so what we know from the atomic number is this: the atomic number of any given element is going to give us two things. It's going to tell us the number of protons in a given element. And it's also going to tell us by default the number of electrons. Right? If the electrons change because you're making ions, the number of protons is not going to change. Right? That's one thing to always remember. Like, the number of protons in the nucleus of an atom will not change. If that atom has a charge, it's going to be due to some manipulation of the electrons in the atom and not the protons, right? So if we know the atomic number, we know the exact number of protons and electrons in a given atom or a given element. All right. And then the atomic mass is a sum. Hopefully you've seen this before, the Greek uppercase S sigma. So it's a sum of protons and neutrons in an atom. All right, sum of protons and neutrons. What if we had the atomic mass and the atomic number, but we didn't know the number of neutrons? Could we solve for it? Right, anytime you have the atomic mass, you can subtract the atomic number from it, and that'll give you the number of neutrons. All right, so you can always solve for the number of neutrons. All right, any questions? All these are just definitions. We're just laying some groundwork for what we're going to do? All right. Are there any questions about anything so far? Anything? So remember, Z is the atomic number, A is the atomic mass, and if you subtract the atomic number from the atomic mass, you will get the number of neutrons in a given atom of a given element. All right, and when do we see changes? If we see changes in the number of neutrons, what do we know about that atom or that element? Is it the original element, or is it something else? If we change the number of neutrons,
Is it something else?
it's something else. It's an isotope, right? I'm just trying to present it to you multiple ways so that when you see it on paper, or when you see it, like when we come Thursday for recitation and you see these different things, then you'll have an idea of the fact that, you know, you can talk about this stuff a lot of different ways and still get to the same conclusion. All right. So now let's talk about ions, because that is part of atomic structure, because the way you make ions is you have to disturb one of the subatomic particles, right? So in order to make an ion, which is a charged atom, right? All it is a charged atom. It could be positive or negative. Can somebody remember when we talked about atoms and charges before? What do we call an atom with a positive charge? Anybody remember that?
You said an ion with a positive charge?
Yes.
Oh, well, you're right there, but it's a cation.
All right. All right. You're right. It's a cation. So that has a plus charge. All right. What about the negative, since you're unmuted? Come on.
Anion.
It's an anion. Good. So an anion is an atom with a negative charge. Cation is an atom with a positive charge. Now let's talk a little bit more about that, because there's a reason why an atom becomes positive or negative. And the reason is the electrons. Again, you can't disturb the nucleus of an atom. Well, you can, but it takes a whole lot of energy. It takes a lot less energy to disturb the electrons, especially the ones in the outer shell of an atom, right? We haven't talked about atomic electron configuration and things like that. But if let me give you an example. So if I have an atom that has let's see, 3 protons in the nucleus and 3 electrons, I'm sorry, 3 neutrons. I'm gonna color the neutrons a different color. And that atom has 3 electrons. That atom is going to have at least 2 shells. We're going to have 2 electrons here in one shell, and then the next shell is going to have 1 electron. All right. So again, with the nucleus being here, and then this being the first shell, we're going to talk a lot about this, so don't panic if it doesn't click right away. And then this being the outer shell, we call that outer shell the valence shell, right? It's the furthest shell away from the nucleus. So you got 3 protons. Let me put some plus charges in here. 3 neutrons. And I'm just making this up, by the way. And then if you got 3 protons, you got to have 3 electrons. All right, so that's going to have at least 2 shells, and the electrons are going to be in those shells. So the way that you make an ion is to disturb the electrons in the outer shell. Whatever shell is the furthest away from the nucleus, those electrons are more susceptible to being moved around. So to make a cation, you have to lose electrons. Now I'm abbreviating electrons as E negative. So from this point forward, if you see me write E negative, that means that's an abbreviation for electrons. All right. In order to make an anion, You gain electrons. Because what did we say the charge on an electron is again? Is it positive, negative, or neutral?
Negative.
It's negative. So the more electrons we add to an atom, and that's not random, you know, you can't just add electrons, but the more electrons you add to an atom, the more negative the charge is going to become. The more electrons you take away from an atom, the more positive it's going to become. Right. So let me illustrate this, but I want to sneak in a reference here to something that you're going to encounter later, and it's called formal charge. Let's talk about that, because you're going to get a really elaborate definition about how to calculate it or process to calculate it. But what we really can do is simplify that down right now, even though we're not necessarily discussing formal charge. We'll do that when we start doing Lewis structures, but I want to just introduce it. All right. So again, a cation is positive, and this is the prefix cat, and then an for the anion. All right. So let's talk about formal charge, because this is a way to think about anions and cations, but it's just in a different way. And you're going to see formal charge a lot, especially when you get to organic. So I'm going to just draw out this molecule. So this is a carbon with 3 hydrogens attached to it. And you have actually, you know what? Let me do this. Let me just use carbon. So I'm going to put a pair of electrons here on carbon. Don't worry about the Lewis structure. We're going to learn that. I don't want to sneak that in because that's a little bit more of an elaborate discussion. All right. But let's see if we can look at this, because this carbon has, when I put that negative, that means that it's -1. If there's no number associated with the negative, then that's telling you what the charge is. So it's understood to be 1. So this carbon has a -1 charge. Is it an anion or a cation? If it's got a negative charge,
Anion.
it's anion. Good, excellent. So this carbon is an anion. The question is, how did it become an anion? Again, in order to, for any atom to have a negative charge, it has to have gained electrons. So somebody look at the periodic table and tell me what we're going to look for 2 things. We're going to look for the atomic number. We're going to look for the group number. And then from the group number, we can determine the valence. In other words, how many electrons are in the outer shell. All right. So somebody look up carbon on the periodic table and tell me what its atomic number is. Anybody? Don't all speak out at once now. We don't want to crash Zoom. So carbon is to the right of the transition metals. If you start at boron, which is B, the next atom next to that is carbon with a symbol of C.
Said atomic number
Yes.
6.
6. Good. So the atomic number of carbon is 6. What's the group number? You see over top of that column, there's a number. There should be a number or a Roman numeral over that column. What is it?
Is it 14?
It shouldn't be 14.
Is it 4?
It should be 4. Yes.
Oh,
the group
4.
number.
It's 4. Okay.
Yeah, that's okay. So
Oh, it's 4. Yeah, it's 4.
yeah, it's 4. So the group number is 4. What the group number is going to tell us is the information we need. And I know this is a roundabout way to get to this, but I might as well lay the whole thing out so you get it. That way you can apply it anytime you need to use it. So the group number is 4. By the same token, that's also the valence number. All right. So the valence number is also 4. All right, now let's go back over here. How many electrons does carbon have around it in this structure? Let's count them up. You have a lone pair. That's 2. All right, let me show you right here. I'm going to draw the bonds in and actually these are covalent bonds. That's kind of ugly. Right? And that means that they have, anybody remember that term, covalent, from like the first or second week of class? All right, that's okay. So these are covalent bonds. Those are bonds with shared electrons. All right. So how many electrons are in each one of those covalent bonds?
2.
2 electrons. Every covalent bond is composed of 2 electrons. Every bond between an atom, if it's covalent, it's composed of 2 electrons, right? So 2 electrons per covalent bond, right? So when we look at the carbon itself, if we're trying to calculate the charge on it, which we are, and trying to figure out why it's an anion, what we do is we take all the electrons that are around it. So when it's bonded, we're going to take 1 from each of these bonds and count it as belonging to carbon. So right now, carbon has a total of how many electrons around it, including the lone pair?
5.
5. Good. Excellent. So 1, 2, 3, 4, 5. Right? So once we know that, and we know the valence, we can calculate the formal charge by taking the valence electrons minus what I like to call the actual electrons. That's just what's around it in the structure. So valence is 4, the actual is 5, and the charge is what? 4 minus 5 is going to be -1. Anybody not following? I know that was a lot, but anybody not following that? So once you know the group number, then you know the valence number. And you can take the valence number and then you can look at any atom and look at the electrons that are around it and figure out what the formal charge is. You're going to see this a lot, not necessarily with the metals, but when we start talking about non-metals and Lewis structures, you're going to see a lot. You're going to see this formal charge calculation a lot. So we might as well do it now while we're talking about cations and anions. All right. Any questions about that? Or about anything? Right. So the way you make cations and anions is by disturbing the electrons in the outer shell. That's how you don't do anything with the protons, anything with the neutrons. It's only the outer shell electrons that get disturbed that cause you to either lose electrons or gain electrons, right? With a cation, which is positive, that means you've lost electrons because electrons have a negative charge. With an anion that's negative, that means you gained electrons because electrons have a negative charge. All right, so this is an example of an anion. Let me show you a cation. And for that, we're not going to do formal charge. We're just going to use a metal like magnesium. So if I have magnesium, what group is magnesium in? Anybody? And you look at the periodic table and tell me what column it's in, what the number over top of that column is. It should be to the far left, right next to sodium or lithium. I'm sorry. Anybody got it yet?
Looking for the group.
Mhm. The column that magnesium is in.
Group 2.
Group 2. It's a group 2 element. Good. It's a group 2 element. What that means is what? The group number is synonymous with the number of valence electrons, right? So magnesium has 2 valence electrons. So if I have magnesium and I wanted to just draw a simple depiction of it, I could draw it like this. If I lost 1 electron from magnesium, and I'm going to do this in a really rudimentary fashion. So minus 1 electron. If I lost 1 electron, what would the atom or the ion look like of magnesium after losing 1 electron? How many electrons would it have left? Look right here. You got 2 right here. Let's say you lost 1 of them. What would the new atom or the new ion look like? You know it's going to be Mg. Is that right? So we're going to lose 1 electron. Wouldn't it only have 1 left?
Yes.
Mhm. What happens to the charge? If making a cation means I lost an electron, what happens to the charge?
Becomes positive.
Become positive. So it's if I lose the 1 electron, this is going to be Mg plus 1. What if I lost that second electron?
+2.
It should go to magnesium, good, plus 2. Anytime you lose an electron, you're going to increase the charge by plus 1. If I lose 1 electron is plus 1, 2 electrons plus 2, 3 electrons plus 3, 4 electrons plus 4, so on and so forth. And this is again an example of a cation, right? So you make anions by losing electrons, and you can make positive a positive ion, which is a cation, or a negative ion, which is an anion. So now let's use all these numbers: atomic mass, atomic number, neutrons, electrons, protons. Let's take that and let's do an example where we have a cation, I'm sorry, of titanium, which is the symbol Ti on the periodic table, has a mass of 48, and it has 20 electrons. Remember, electrons do not contribute to the mass. Sorry about that. I don't know why my thing just dropped. But let me do this. Y'all pray for AT&T because I'm cussing them out today in my own way. Come on. Okay. So the titanium cation has a mass of 48 AMU, and it has 20 electrons. The question is, what is the charge? And how many neutrons are present? All right, so let's deal with the charge part first. How do we know, how could we determine the charge on any atom, right? What is the charge going to be directly connected to? We just talked about it. If it's going to be an anion or a cation, what number is going to be indicative of that? What gets affected when you make anions and cations? Do the protons get affected? Do the neutrons get affected?
The electron.
The electrons. Good. So now we can figure out how many protons are present using the mass number and the atomic number. So somebody look up the, we know what the atomic mass is. So the atomic mass is 48. That was given by in the problem. What is the atomic number? For titanium, it's in the middle. It's a transition metal in that long rectangular block between the right side of the left side of the periodic table and the right side. And the symbol is Ti.
22.
22. Good. What that number tells me is what? How many protons are present in a titanium atom? Because that's what the atomic number tells me. Is that right?
Correct.
Mhm. So how many protons? There's 22 protons. Has to be. If the atomic number is 22 and the protons don't get affected by ionization, then we don't care about the electrons being lost or gained. That number never changes. So if I have 22 protons, the way that I can determine the charge is I can take the protons and subtract out the electrons. Does that make sense? Because that's going to tell me how many electrons I actually lost. Let's say that the titanium was neutral. How many electrons should it have if it was neutral? Think back to, we talked about it at the very beginning of the class. For a neutral atom, how many protons and electrons should it have? Let me not say how many. Should they be equal if it's neutral? Since one is positive and one is negative?
Yes, because they even out.
Yes, they should even out. Good. Because if atom is neutral, it should have the exact same number of protons and electrons. If it's not, if it's an ion, it's going to have the same number of protons, but the number of electrons is going to change. So to figure out the charge, let's put that number in. So we know we got 22 protons. How many electrons based on the question? 20 electrons. Is that right? So is that number is going to be +2. So the charge on that titanium atom with 20 electrons is +2. Now we can also figure out how many neutrons are present by taking the mass, which is 48, and subtracting out the atomic number. So this is atomic mass, this is atomic number, and we get 26 neutrons. But I want to go back to the other part to make sure we understanding that. If we know the number of protons and the number of electrons for any atom, we can determine whether it's neutral, whether it's an ion, cation, or anion, right? If it's neutral, the protons and electrons should be equal. If it's negative, they're going to be more electrons than protons. If it's positive, they're going to be less electrons than protons. All right. Does that make sense?
Yes, sir.
I'm gonna put it in here and then we're actually gonna stop right here. If I could spell neutral, I can't put that on YouTube. So neutral, protons, electrons are equal. positive. Protons and electrons, well, they have less electrons. Right? Everybody following that? Electrons are less than protons. We okay with that?
Yes, sir.
All right, and then if it's negative, then the number of electrons are going to be greater than protons. Right, so you can find out the charge on any atom if you know the number of, if you're given the number of electrons. If it's telling you that it's an ion and it gives you the number of electrons, all you need is the atomic number to figure out the charge. Right, so it's the atomic number minus the number of electrons, and that'll give you the charge. All right, we got to stop because it's 1:51. This morning I had a chance to actually introduce the periodic table, but I can wait and we'll do that on Wednesday. All right, any questions about anything we just talked about?
No, sir.
All right,